Let's talk about conditional introduction and elimination. The basic idea motivating conditional elimination is this. If you know that P, and you also know that if P, then Q, then you can infer Q. So for example, if you know that Alice did great in the exam, and you also know that if Alice did great in the exam, she must be very happy, then you can infer that Alice must be very happy. This is a very famous, often discussed rule of inference, and it has a special name. It is called modus ponens. Formally, modus ponens, or conditional elimination, looks like this. If in line M of your proof, you have a sentence of the form A, and if in a different line N of your proof, you have a conditional whose antecedent is A, then you can infer the consequent of that conditional, in this case B, and justify this inference by citing conditional elimination applied to lines M and N of your proof. So here are a couple examples of correct applications of this rule. First example, suppose in line M we have the sentence if A then B, and in line N we have the sentence A, then you can infer B. Second example, if in line M you have the conditional A, if A or C, then B, and in line N you have the antecedent of this conditional, A or C, then you can infer the consequent B. As before, the order of the lines M and N doesn't really matter. So suppose that in line M you have the sentence A or C, and then in a later line of your proof, line N, you have a conditional of the form A or if A or C, then B. You can still infer the consequent of this conditional B, even though the order of these two lines is reversed in comparison to what we have seen before. Now, to look at our fourth and final example, suppose that in line M of your proof, you have a conditional whose antecedent is a conditional. So suppose that in line M of your proof, you have the sentence if A then B, then C. And suppose that in a later line of your proof, you have the antecedent of this conditional, if A then B, which is itself a conditional. You can then infer the consequent of your conditional in line M and justify this inference by citing conditional elimination as applied to lines M and N. Now, the basic idea motivating conditional introduction is this. If under the supposition that P, you can infer Q, then you can conclude that if P, then Q. For example, suppose that Atari is a cat. You can certainly infer that Atari is a mammal. So you can conclude that if Atari is a cat, he is a mammal. Formally speaking, conditional introduction looks like this. If under the supposition that A, you can infer B, then you are licensed to infer the conditional if A then B and justify this inference by citing the rule conditional introduction as applied to lines M to N. Now, in this statement of the rule, you will notice the use of a subproof. So this second vertical line to the right of our main vertical line introduces a subproof into our main proof. Now, we start subproofs whenever we introduce additional assumptions into our proof. When you use conditional introduction, you introduce an additional assumption into your proof. In this case, you introduce the assumption A. And then you go on and you show that under the assumption that A is true, you can infer B. And this entire subproof that starts with the assumption that A and ends with the conclusion that B, then licenses you to infer that if A, then B. So here are two examples of correct applications of the rule conditional introduction. The first example is this. If under the supposition that A, you can infer B, then you are licensed to conclude that if A then B, and justify this inference by citing conditional introduction applied to lines M to N. Here's a more complex example. Suppose, if under the supposition that A or B, you can infer the conditional if C then D, then you are licensed to conclude that if A or B, then if C then D. And you can justify this inference by citing conditional introduction as applied to lines M to N. So here's our first example of a Fitch-style proof. We are proving that the conditional if S then T follows from the conditional if S then T and S. Now this should be valid, right? If S entails that both T and S, then sure, S should entail that T. Now how can we prove that? I'm going to number my one premise and number that line using the numeral 1. I have drawn the Fitch bar under my premise. And now I'm going to start thinking about how I can infer this conclusion. Now I see that this conclusion is a conditional if S then T, and that suggests to me that I may be able to infer it using conditional introduction. Now conditional introduction requires me to use a subproof. So let's just imagine, it's so to speak, I'm expressing a wish here. Let's suppose I am able to prove that T from the assumption that S. If I'm able to do this, then I will be able to infer if S then T, citing the rule conditional introduction and my subproof from to question mark. I'm also going to put a question mark here to remind myself that I have not yet actually proven T. This is just on my wish list. I want to prove T, but I have not yet established that T. So how can I infer T? Well, let's look at what we already have. In line 1, we have the conditional if S, then T and S. And in line 2, we have S. Using these two lines, I can infer T and S, citing the rule conditional elimination, and lines 1 and 2. So I've here inferred the consequent of my conditional, given that I know that the antecedent is true. Or I've supposed that the antecedent S is true. Okay, so we have established the conjunction T and S. Now I have an idea for how I can prove T. Because of course, if the conjunction is true, then either conjunct must be true. And I can infer the first conjunct T, citing conjunction elimination and line 3. So what I've done in this subproof from 2 to 4 is I have shown that under the supposition that S, it follows that T. And that means that now I can infer the conditional if S then T, citing conditional introduction and lines 2 to 4. And that's our complete proof.